Hello, and welcome to this webinar sponsored by E1 Utility Systems, Hydrogen Safety Best Practices for Large Turbo Generator Gas Monitoring and Purging, with Steve Kilmartin, Director of Products and Markets at E1. My name is Andrea Hauser, and I'm the Managing Editor of Energy Tech Magazine. I'll be your moderator today. Hydrogen is becoming an increasingly popular coolant medium for large turbo generators due to its better heat transfer characteristics and low density. But while it is 14 times more efficient than air at heat removal, it can be very dangerous if not used properly, as recent catastrophic events have shown. Today, Steve Kilmartin will discuss the pros and cons of using hydrogen, methods used to measure gas purity and dew point, as well as other issues to consider. Steve has more than 30 years of experience in power generation and is a leading expert in the field of generator monitoring and maintenance, including work as a principal investigator for the EPRI Turbine Generator Auxiliary Systems Volume 3 Generator Hydrogen System Maintenance Guide. He has worked for E1 since 1998. Steve, please begin.
Thank you. As Andrea mentioned, I will be presenting on hydrogen purity and moisture monitoring in hydrogen-cooled generators. And because of recent events at several U.S. utilities, I will be spending a bit of time on measuring gas purity during the purging or gassing and degassing of these hydrogen-cooled generators. Everything in this presentation is about safety, efficiency, and risk mitigation. We will be discussing hydrogen as a cooling medium, the importance of purity monitoring, the gassing and degassing process of a generator, and the importance of dew point monitoring. In the late 1930s, there was an increasing demand to get more megawatts out of a generator. With generators, more megawatts means more iron. They get physically larger, and they also generate more heat. In order to satisfy the demand for power without increasing the generator physical size, a different cooling medium was required. I find it interesting that someone decided it would be a good idea to cool a generator with hydrogen. However, the idea worked, and now all large generators are cooled with hydrogen or with a combination of hydrogen and water. Why hydrogen? Because it takes less horsepower to produce more power. Hydrogen has less windage and frictional losses. The relative density is 4 times less than air. Hydrogen has better heat transfer characteristics. It's 14 times more effective at removing heat from these components in the generator that are heating up. The bottom line is you get more megawatts per pound of iron when you're cooling with hydrogen. This chart indicates the density and specific heat transfer characteristics between air and hydrogen. You will note that hydrogen at 45 psig is 4 times less dense than air, and the specific heat capacity is 14 times greater than air. Again, meaning that hydrogen is much better at removing heat from the components inside the generator that are heating up, and also because it's less dense, you can turn the generator easier. There are additional benefits in using hydrogen as a cooling gas. Because it's a sealed environment, less contaminants will get into a generator versus an air-cooled generator. Because it's a pressurized vessel, the pressure suppresses partial discharge and increases the level of voltage required for component breakdown. Oxygen or hydrogen is not an oxidizing agent, which means there's no corrosion that would take place. Pure hydrogen will not support a combustion. And that's very important to note, that pure hydrogen that will not support combustion. Also, because bottled hydrogen and bulk hydrogen is typically very dry. The moisture or dew point in the generator will be very low. One of the problems with using hydrogen is you have to keep the hydrogen in the generator case. And because hydrogen molecules are so small, they are hard to contain. This slide indicates a sectioned view of a hydrogen-cooled generator. The outer shell is what seals the hydrogen in. This is a sealed iron case. One area where it's difficult to seal the hydrogen is around the rotating field or rotor. There are hydrogen seals on both ends of this generator that I'm pointing out right now. That's what keeps the hydrogen from leaking out through the rotor body. You will also note that there's 2 fans on this generator, one on each end. These fans are used to circulate the hydrogen in the generator. This becomes important when we discuss where the hydrogen sample should be taken. And it's important to note that one side of the generator fan will be at a high pressure and the other side will be at a lower pressure. This is a sectioned view of a hydrogen seal. You see where the oil flows into the seal. It hits the rotor shaft, and this is what's forming the seal. There's oil between the seal and the rotor. The oil will flow in 2 different directions. It will flow towards the outside of the generator or the air side of the generator. The oil will also flow towards the inside of the generator or the hydrogen side of the generator. You can see that the seal oil on this particular seal is at 95 psig, whereas the hydrogen is 90 psig. Hydrogen being at a lower pressure allows the oil to flow in towards the hydrogen. And then it's captured, and the oil on the hydrogen side and air side is returned to the hydrogen or the oil tank. This is what we're trying to avoid. No one wants to be at work and have this happen. What took place with this generator is there was a hydrogen leak through the seals, and the hydrogen leaked into this collector cab, which used to be next to the generator. So hydrogen leaked into the collector cab, and then you have the 3 things needed for combustion. You have the fuel, which is the hydrogen that leaked from the generator. You have air or oxygen that's inside the collector cab, and then you have the ignition source, which in this case was the arcing or sparking that was taking place from the collector rings inside the collector cab. And then what happened as the hydrogen started on fire, then the seal oil started on fire, and the problem just escalated. Why do we monitor hydrogen purity? I think the first and foremost reason is safety. Hydrogen is explosive when mixed with air between the range of 4 to 75%. It's most explosive at about 13%. We also monitor the hydrogen purity because of efficiency. We like to keep the hydrogen 90% or 96% or higher. This makes the generator more efficient. We should be monitoring the gas purity during the gassing and degassing of the generator and during the normal operation of the generator. We could also add risk mitigation to this. We have safety and efficiency. We could add risk mitigation to this also. As you've seen in the previous slide, that hydrogen leak caused that generator to come offline. This graph represents the effects of hydrogen purity versus windage loss versus financial loss. You can see on this graph that if you go from, let's use the 800 megawatt, by the way, this is typical. This is for each generator and each power plant. This will vary. But you can see at 91%, if you go from 91% down to 99%, there's a significant change in the windage loss in that generator, greater than 3,000 kilowatts. And then if you convert that into financial losses, if you could be losing on this particular generator $4,000 a day because of that change in hydrogen purity. This is a typical P&ID for a hydrogen system on a generator, and I just want to point out a few features on this P&ID. On the top right-hand corner, you have the gases that are used in this generator. You have CO2 supply, H2 supply, and air supply. On this particular generator, the air is fed into the generator through the same line as the hydrogen generator. There's debates in the industry and with OEMs which is the best way to bring air in, through the hydrogen header or the CO2 header. On this particular P&ID, the air is coming in through the top header, which is the supply header, H2 supply header. We'll be discussing that later in detail. And then the gas goes through the manifold, and then it exits out this cabinet and goes to the generator through these connections on the lower right-hand corner. Some other features on this P&ID, you can see that we're measuring CO2 supply pressure. We've got a pressure indicator gauge and a pressure transmitter. Transmitter feeds a signal back to the control room or the Mark 5 or Mark 6, whatever is used on the generator. The H2 supply pressure, we're measuring the pressure with an indicator and a transmitter. Here you can see where we're taking the sample for the analyzer. The hydrogen sample comes in through the fan pressure, through a filter and moisture indicator, goes around a three-way valve through a flow meter into the analyzers. Here's our purity analyzer. Then it goes to a three-way valve and back to the generator through the fan suction. We are also measuring case pressure with an indicator and a transmitter. We are measuring fan differential pressure with a indicator and a transmitter. And on some units you can actually compare the fan differential pressure and it can be converted into purity. If the fan differential pressure is not sufficient to get a flow through the analyzer, we can divert this three-way valve, take the sample, and then the sample goes out through the vent. And that allows us to have enough flow through the analyzer. On the bottom you can see that on this system they have their calibration gases hard piped into the system. You note that the calibration gases do not go through the filter. That's very important because the filter, some filters can absorb CO2 so that when you're calibrating with CO2, the filter absorbs it. Then when you go to read hydrogen purity, the CO2 will outgas from the filter and cause a misleading reading. You can also note on here that this analyzer can take a sample from the purge connection. The purge sample should be taken from the vent. Here the line comes through. We would change the three-way valve, go through the flow meter, and then back into the analyzer. That would allow us to read the gas when we're purging the generator. And I'll point out that there's two different locations where samples should be taken. You should be taking samples across your fan suction and pressure during normal operation, and then during purge operation it should be taken from the vent line of the manifold. You can also note on this that there's a connection for the portable gas analyzer, which I recommend be used during purging of a generator also. This is a rendition of a typical generator gas analyzer panel. This is the control panel used to control the analyzer. This flow meter controls the flow through the analyzer. You have on this particular panel, we have a generator differential pressure gauge to measure the fan differential pressure. We can also measure the case pressure. We have a moisture indicator, which is on the output of a filter, and the filter is used just to protect the sensor. That's the only purpose of the filter and the moisture indicator. Important to note that this control panel is intrinsically safe, meaning it can be used in a hazardous area. Very important when you are speccing out a new analyzer that the analyzer be third party or be certified to be used in a hazardous area. This slide lists some of the technologies used to measure purity. A manometer, which in the old days was a glass U-tube filled with mercury. It was used to actually measure the differential pressure, and then you use the DP and a graph that was supplied by the OEM supplier to convert that DP into purity. This manometer was connected across the fan differential or the fan on the rotor of the generator. A gas density blower also measures differential pressure, and the differential pressure is then converted into gas purity. There are different types of thermal conductivity analyzers. The one thing they have in common is they all use a thermistor as their sensing device. However, thermistors from different models will vary. Some are more accurate, some are faster to respond, and the electronics can vary considerably. And then there's a newer type analyzer out there that uses a vibrating element to monitor hydrogen purity. Things to consider when speccing out a purity analyzer, first and foremost, is accuracy and stability. You want the analyzer to be accurate. You also want it to be stable. You don't want to be recalibrating this every week or every month. Analyzers should be able to be calibrated and go 6 months to a year without being recalibrated. You want the analyzer to be a triple range analyzer. If you're using CO2 as a purge gas, then you want it to measure air and hydrogen, or hydrogen and air. You want it to measure hydrogen and CO2, and you want it to measure air and CO2. The analyzer should be located where you're getting a good representative sample, where it's not, the flow is not being restricted. You should have filtering on it to prevent oil from getting into the analyzer. And probably most important, it should be classified to be used in a hazardous area. And depending on the country, different countries have different requirements. In the United States, you would have to meet North American Electric Code Class 1 Division 2 Group B. In Europe, it may be ATEX that it should be certified to. In Australia or South Korea, it may be IECEX. Now I'm going to talk about purging the generator, and because of recent events that have taken place in the United States, one, there was a major explosion, the other one, there was actually a loss of life, and I'm going to spend some time on this. The first thing that you need to make sure of is that the standard operating procedure is updated and understood. And the same goes with the P&ID. The P&ID has to be current. The reason I say this is because years back, they would have outages every year, every 2 years. So the same people were doing the purging all the time. It became repetition. With nowadays, outages are going 5, 6, 7, up to 10 years. So the person that did the purging at the last outage might even not be employed anymore. So it's very important that the standard operating procedure be updated, be understood, and that the P&ID be current, inaccurate. You need to verify that the valves are properly labeled. This goes along with the P&ID being current and accurate. And the way that you do this is you trace the pipe from the generator and physically make sure that everything is in the proper location and is labeled properly. You should verify that your generator gas analyzer is operating properly. You may even want to recalibrate it before the purging process. I also recommend that a portable gas analyzer be used. This gives you a redundant reading, gives you 2 out of 2 voting so that you can make sure of the purity that is actually in the generator. These last 2 items, the portable hydrogen sniffer and the liquid leak detectors, again, because outages are going out in years, 5 to 10 years, these valves are not being exercised. So when they are exercised, there is a chance the packing dries up and that they could leak. So very important that you have portable hydrogen sniffer or leak detector available when you're exercising these valves to make sure that you have no leaks, no hydrogen leaks in the area. The one point I got at the bottom, operations and I&C involvement. I've been at several plants where the purging process is actually carried out by operators and the I&C people. And I think it's important that you have 2 people present when you're doing this process so that one can read the standard operating procedure and look at the P&ID, while the other one is actually tracing the valves and looking at the valves and controlling the valves. 2 heads looking at this is very important. This is a simple view of a section of a generator. The reason I have this up here is to show that you have a hydrogen distribution pipe that's inside the generator that is used to feed hydrogen in the generator. And as I mentioned earlier, this pipe may also be used to bring air into the generator. Then there is a bottom distribution pipe that is used to put CO2 in the generator, and there are some utilities, some OEMs that will bring air in through the CO2 distribution pipe, which when I'm discussing purging the generator in these later slides, I will be bringing the air in through the carbon dioxide or distribution pipe. And then you can see the feed lines that come to these 2 distribution pipes. And then over on the side, on the left-hand side, there are lines that feed the hydrogen analyzer, and this is during normal operation. This is when the generator is turning. These are connected across the fan differential pressure and the fan differential suction. That's what, there's a flow from one pipe to the other. That's what creates the flow through the analyzer. I'm going back to this P&ID just to point out that when we use air and we put air through the hydrogen line, there's advantages and disadvantages to this. The one advantage is that air going out the top header allows the heavier CO2 to blanket and push the air out. The potential disadvantage is in this section that I'm pointing to right now, you will have hydrogen in there when you change this spool piece over to air. And so you will have an air-hydrogen mixture for this small area. Over the years, this has not been a problem. I'm not aware of this ever being a problem. However, because of those recent events, there's more caution being put into making sure that air and hydrogen never come in contact with one another. One thing to note when you're purging a generator is that your CO2 should be entering the generator slow because you don't want to create a thermal shock to the generator. When CO2 moves at a rapid rate, it can become cold or freeze. And you also want to make sure that you're using clean and dry air. This is a rendition of a hydrogen control cabinet that has the manifold. This is the panel that we looked at before. This is the control for the analyzer, the fan differential pressure gauge, the case pressure gauge. These are the valves that control the flows into the analyzer cell. On this, you also have the CO2 supply pressure, H2 supply pressure, and here's the manifold that's used to put the gas in and out of the generator. You can see the connections on the top. These connections go to the supply gases, and these connections in the back go to the generator. They're the gases. They're the connections that feed gas into the generator. And then this valving is used to control which gas which is flowing in which direction. This spool piece here is to assure that you do not put hydrogen and air in the generator at the same time. In one position, it will allow hydrogen to come in the generator. You have to physically disconnect it and move it over to here in order to put air in. So it's impossible to bring air and hydrogen into the generator at the same time. This is a picture of a portable analyzer. As I mentioned, I do recommend that a portable analyzer be used during the purging process just to give you a second reading on what the gas is that you're purging. This portable analyzer is designed to be used in a well-ventilated, safe area. Now we're going to discuss the actual purging of the generator. And one thing I need to make clear here is that this is a very general process that I'm discussing. This is not to be used in a power plant as a standard operating procedure for purging a generator. When in the process that I'm using here to purge this generator, I'm going to use CO2 as my purge gas, and also air, instead of coming into the top header, pushing CO2 out of the bottom header, is going to be coming into my CO2 header in the bottom. This will require more air to be used because of the mixing that's going to be taking place, because you're no longer maintaining that blanket. The first thing that we're going to do is set this up for an air test. So you will note on the side that the two spools, that the spool piece for the CO2 and the spool piece for the hydrogen is going to be removed, and then there's going to be a spool piece put in for the air. The valves are open to allow air to go into the generator. And as I said, the air is going to come into the CO2 header, the bottom header. The generator becomes pressurized with air. And then we shut off the valves and they do their pressure test. Now I've got air in the generator. I've got pressurized air in the generator. I had air in the generator before, and now I got pressurized air in the generator. Now I'm going to fill the generator with CO2. I'm going to push the air out and put CO2 in. You will note that this spool piece is going to be taken off for air, and the spool pieces will be put in for hydrogen. And now my valves are open for the CO2 to be allowed into the generator. Also, my valve for the vent line now is open so that I will get a flow out of the top header, out the vent line, and to my analyzer. And it's important that normally, during normal operation, my analyzer is being fed through these lines. During the purge operation, you want to take your sample from the vent. I'm sorry if I said this was vent. These are across the fan differential on the generator. When you're taking a sample during the purge, you want your sample to come from the vent lines. So then the CO2 comes into the generator, comes in through the bottom header, fills the generator up, and then goes out the vent of the generator. And again, I'm taking my sample at this point. Now, if I took my sample over here, as soon as I started to put air in, or CO2, because CO2 is so heavy, if I was taking my sample here, I would read CO2 almost instantly, as soon as I got CO2 on the bottom of the generator. That's why it's important to take the CO2 reading from the vent, because now CO2 has to completely fill the generator before I see that I've got pure CO2 in the generator. Now I'm going to fill the generator with hydrogen. The valves are opened up to allow hydrogen to come into the generator. They're also opened up on the bottom header to allow the CO2 to exit and hydrogen to fill the generator. Now I got hydrogen coming in, comes into the top header. It's a lighter gas, pushes the heavier CO2 out the bottom header. Out the vent line. So now I've got the generator filled with hydrogen. I'm sure that I've got it filled with hydrogen from my analyzer reading. And now I'm going to operate the generator. Okay. And you can see now during normal operation that I'm taking my hydrogen feed or my purity feed across the fan. Now when I want to get rid of the hydrogen, or I want to purge my generator to go into an outage, now I'm going to do a CO2 fill and get rid of the hydrogen. You can see that the valves are opening now for my CO2 to come into the generator. My vent line is now open so that I can dump the hydrogen out of the generator. And now my CO2 is filling. Again, my heavier CO2 is coming into the bottom header. Generator is just pushing the hydrogen out of the top header. And then the hydrogen goes to vent. And now I'm taking my hydrogen reading, or my gas purity reading, over in the analyzer on the vent connection. I'm no longer using the fan pressure and suction to supply gas to my analyzer. Now that I've got hydrogen or CO2 in my generator, I'm going to fill the generator with air. You'll note that the spool pieces now will be taken out to prevent air and hydrogen from mixing. I'm putting in my spool piece for air. And now I bring air into the generator. And as I mentioned, I'm bringing air in through my CO2 header. There are procedures that bring air in through the hydrogen header. However, that does mix a small portion of hydrogen and air in the piping. And now I'm back to having my generator filled with air, and it's safe to open it up and do work on it. Now we're going to talk about monitoring dew point. Why do we monitor dew point? And the main reason we monitor dew point is, in my opinion, component and insulation failure. High dew points can cause corrosion, can cause insulation failure. What is a good dew point? A good dew point is about 0. 0 degrees C. Most OEMs will use 0 degrees C as my alarm point as to when I should take action if it goes above 0 degrees C. It's important to note that, again, that hydrogen that's coming from bottles or bulk systems is usually very dry. And hydrogen that is supplied through a hydrogen generator, a machine that makes hydrogen, that is always very dry. Now, we also have efficiency on here. I'm not certain about this, whether we monitor dew point because of efficiency. It makes sense that if I've got moisture in my hydrogen, I'm going to have greater windage loss. However, I'm going to show you a chart that says that the difference between, for instance, plus 5 degrees C and negative 5 degree has minimal effect on the density of the hydrogen. Increased dew point can support insulation failure, electrical tracking. There's a great paper that's written by Generator Tech, the late Don Albright, that discusses this in detail. If anyone is interested in that, they can get in touch with me, and I can certainly supply them with that paper, or you can get it from Generator Tech also. Also, increased dew point will cause corrosive effects, especially on the retaining rings, but also on the rotor body. The retaining ring is the most highly stressed mechanical component in the generator. So it's very important that the strength of that retaining ring be maintained. There were rings put on generators that were made out of 18.5 stainless steel. These retaining rings, or this material, was highly affected by moisture, and there could be corrosion or cracking that's caused by the moisture. With baseload generators, you have a constant warm temperature in the generator. Because more recently generators are being used as peaking units, or the loads are changing on these units, these load changes will not create the moisture. However, what will happen is it will increase the chance of condensation forming because of the moisture that's already in the generator. This is a picture of a failed retaining ring. Again, this is not what we want to see in our generators. This slide shows the retaining ring failed. Again, the retaining rings are the most highly stressed mechanical component in the generator, and you need to make sure that the integrity of those rings are maintained. Not only does it destroy the ring and have effect on the rotor, but in this case it took out the end windings and the windings of the generator. This is an example of some shorted turns. This is where the turns are underneath the retaining ring of the rotor. In this case, the retaining ring has been removed, and you can see where there's a breakdown of the insulating material. Moisture, along with other contaminants, can form conductive bridges, which can lead to electrical tracking, cause the insulation to deteriorate, and cause a coil-to-coil short. Again, there's an excellent paper written by Generator Tech that discusses this in detail. This is that chart I was talking about. You can see from the blue line that any change in hydrogen purity will have a major change in density. Here we go from 95% to 99%, and you can see there's quite a change in my density of my hydrogen. However, with dew point, here if you go from plus 5 to negative 5, and as I said, the cutoff is, most OEMs will use 0 degrees C as the alarm point. If I go from 5 to negative 5, I have very little change in my hydrogen density. And that's why I'm saying that unless you have a major increase in your dew point, or your dew point goes up a lot, it's going to have little effect on your hydrogen density. Where does moisture come from? The primary source is the seal oil. In many large plants where you have steam turbines, the steam turbines and generator will actually share oil. And if the vacuum system's working properly, there should be no issues. But steam will put moisture into the oil. When the oil is used on the seal of the generator being dry will actually absorb moisture out of the oil, actually act as a sponge and pull moisture into the generator. So the primary source for moisture is the seal oil. You can also get moisture from your hydrogen coolers. However, usually this is a major leak and you'll detect it in your liquid level detectors. You can also get moisture into the generator through your, if the stator windings are cooled with water, there's a clip where the water is brought into the stator winding. These clips sometimes leak, and you can get moisture into your hydrogen through a clip leak. And as I mentioned earlier about the thermal cycling isn't a source of moisture, but if you do have moisture in your generator and you're thermally cycling, there are more chances that you will have condensate form in your generator as a result of having moisture in there. There are many different kinds of sensors that are used to monitor dew point. You have a ceramic chip or a ceramic sensor, silicon-based sensor, aluminum oxide sensor. I'm not aware of chilled mirrors being used in a hydrogen-cooled generator, although chilled mirrors are a standard for measuring moisture content in the atmosphere. All of these sensors, with the exception of the chill mirror, you're measuring a change in electrical properties, whether that change be capacitance, resistance, or impedance. Considerations for a dew point analyzer is similar to that as a purity analyzer. You want to make sure that it's accurate. You want to make sure that it's stable. You don't want to have to keep recalibrating these units, and obviously you want an accurate reading. You need to know that if you have to compensate for the pressure, being that if the sensor is calibrated at atmosphere and then you put it in the generator, now you got a different pressure. So you may have to compensate for that change in pressure. You want it to have minimal effect as a change of temperature or case pressure. If there is an effect, you want to know how to compensate for that. Again, the sample location should be good so that you're sure that you're getting a representative sample. You want it to be located where you're not going to get oil in it if the oil gets into the generator. On filtering, you want to filter out oil, but you want to filter out the moisture. So you got to be careful in selecting the filter that you use to remove oil from keeping oil out of the sensor. You want to make sure that you got a good flow going to the sensor. And again, the area classification. You want to make sure that this analyzer is rated to be used in a hazardous area. And again, in North America or in the United States, you use the North American Electric Code, Class 1, Div 1, Group B. In other countries, you would use there's different standards that you have to meet. In summary, or in closing, by using hydrogen as a cooling medium, you can get more megawatts without increasing the size of the generator. Again, more megawatts per pound of iron. For reasons concerning safety, efficiency, and risk mitigation, it's very important that we know the gas purity during all phases of operation of the generator, whether it's during operation or whether it's during the purging of the generator. Before gassing and degassing a generator, make sure that your standard operating procedure is up to date. Make sure that it's understood. Make sure that your P&ID is up to date and understood. And as I said before, I think it's a very good idea to have two parties involved when you're purging the generator. and maybe it's even a better idea to have someone from operations involved and someone from the I&C department involved. It is very important that we know the dew point in a generator to mitigate risk. High dew point in generators can cause component failures. This is all about safety, increased efficiency, and risk mitigation. Thank you.
All right. Thank you, Steve. And now we have about 15 minutes for some Q&A. So if you have questions for Steve, please feel free to submit them under the questions toolbar in your GoToWebinar toolbar. Our first one is from William, and he is wondering how many fill and vent cycles are recommended to ensure that the generator is either full or clear of hydrogen.
Could you just say that one more time?
How many fill and vent cycles are recommended to ensure that the generator is either full or clear of hydrogen?
It's only one cycle per gas. As an example is that if I've got air in the generator and I want to purge the air out and put hydrogen into the generator, I'm only putting CO2 in because CO2 is an inert gas. I'm putting CO2 in to get rid of the air, and I'm only doing this once. Now, that may take several hours to do that, but I'm only putting the CO2 in. It's once. It's only going in through one cycle. And then when I'm putting hydrogen in, obviously I'm bringing the hydrogen in and I'm putting CO2, taking the CO2 out. Once I got hydrogen in there and I start my generator on whether turning gear or I'm going online, there may be pockets of CO2 in there that will come out and it may affect my purity, but when I'm online and when I do have hydrogen in the generator, I'm constantly feeding fresh hydrogen into the generator anyways. But I want to stress the importance of not only using your normal analyzer to measure the gas purity during the purging process, but also using a portable analyzer so that you have a redundant reading as to what that gas purity is to make sure it's safe to go into it.
Okay, great. And then Anthony is asking, how accurate is it to measure the purity with a manometer compared to an analyzer?
I really couldn't answer that. The only thing I can say is that years ago, or when hydrogen-cooled generators were first used, using a manometer to measure the differential pressure and then taking that differential pressure and using a chart that was provided by the OEM to convert to purity, that was the standard. That's what all generators had on them were manometers. But I'm not certain of the accuracy. I can't imagine actually that it would be that accurate. I've seen these in the field, and to read 15 inches or 16 inches of DP in a generator with a manometer, it's difficult to tell if it's 15 or 15.3 or 14.7. Manometers are not that, or do not lend themselves to being that accurate.
Okay, great. And then Michael had a question about what is the smallest capacity generator where hydrogen cooling is recommended?
I've seen generators as small as 25 megawatts. That's very unusual, and they were very old generators. But I've seen them as small as 25 megawatts. It depends on the OEM or the generator manufacturer as to what size they will cool with air, what size they will cool with hydrogen, or what size they will cool with a combination of hydrogen and water. For instance, General Electric will make generators that are hydrogen cooled that are in the neighborhood of 100 megawatts. Siemens and Alstom will make generators that are 250 megawatts, and they will be air-cooled. So it really depends on the generator manufacturer as to when they start to cool with hydrogen or when they cool with air. Again, General Electric will start cooling with hydrogen around 100 megawatts. Siemens and Alstom will start to cool with or will cool with air up to 250 megawatts.
Great. And then Tony had a question about if there is a temperature that they should make sure the generator is below before purging.
Boy, that's a great question. I am aware that I can't answer that. If the question is submitted, I can find out the answer to that. But it is my understanding that the generator should be at its normal operating temperature at a minimum before you no higher than that before you start purging the generator. But the reason that that's such a good question is that if I've got a generator that's just coming offline and it's still warm, and I'm putting cold CO2 into that generator, that could cause thermal shock into the generator. So I have to be very honest. I don't know the answer to that.
Okay, but that's something that Tony can get in touch with you about. And
absolutely, and I can find out the answer.
Fantastic. Then we have a question from James, and he is wondering, can H2 pockets be present, such as in the bushing box at the low point on the generator? And if so, is there a recommendation for purging prior to opening?
The chance of having CO2 in the pocket, especially on the leads down on a generator where the leads come out of the bottom, is certainly a possibility. As a matter of fact, it's very likely that you're going to have CO2 in the bottom of the generator. If the generator has a drip leg that's connected to the bushing box. Some generators have drip legs that are, or liquid level detectors that are connected to the bushing box. You could use that line to purge out the CO2. And I would make sure that if you have hydrogen in the generator and you're purging the CO2 out of the bushing box, you want to make sure that the connection to the liquid level detector or the drip leg is going to a well-ventilated, safe area during that purge process.
Okay, and then we have a couple questions from some of the viewers about what kind of filter is recommended for the hydrogen. For a hydrogen filter or for, I'm sorry, go ahead.
We use, the filter that we use is a coalescent filter that will remove both oil and moisture. Now this is on the purity analyzer, not on the dew point. We use a coalescent filter that will actually remove both moisture and oil. What I would recommend, if you're looking for either contact environment one, we can tell you what we use on our equipment, or you can contact companies such as Parker that would make a recommendation also on what filter should be used. Where this becomes critical is on the dew point. You don't want to you don't want to remove moisture in that filter before it goes to the dew point sensor. However, on a purity analyzer, you do want to remove the moisture and the oil. You want to protect the sensor.
Okay, great. And then we have a question from Norberto, and he's wondering, while filling or purging an H2 cooled generator, is it better to keep the rotor in turning gear, nominal speed, or just standstill?
Definitely not nominal speed. I've discussed this with people, and I've been told that turning gear helps get rid of some of the gases that could be in pockets mainly in the rotor, where you may have air or CO2 get trapped in the passages, the cooling passages in the rotor. So it is probably preferred to do the purging while you're on turning gear. However, before I did that, I would go to my OEM and get their recommendation and make sure that it's all okay with them that they purge while the generator's on turning gear.
Okay. And then Franklin is wondering, what concerns are there about discharging H2 to the environment from a safety standpoint?
When the hydrogen is discharged into the environment, where the path that it takes is it comes from the generator, goes through the hydrogen control cabinet, and then the hydrogen control cabinet is tied to a main vent line. Some of these are in the neighborhood of 4 to 6 inches in diameter, and this vent line goes up through the roof of the turbine hall and exits out the top of this roof into atmosphere, into a well-ventilated area. It's absolutely critical that that's how this takes place. You certainly do not want to be venting hydrogen anywhere else other than through this vent line and out the roof of the turbine hall. You want to make sure you're outside.
Okay. And then one last question from Roger. If you have a complete failure of your AC and DC seal oil pumps or a hydrogen seal failure, have you any advice about carrying out an emergency degas?
There are manufacturers that actually will provide units with purging, the emergency purging of the system. The one thing that you have to be, at a minimum, what I would do is open my generator to vent so that I'm venting that hydrogen that's remaining in the generator out through the vent. But there are products on the market that allow you to do a rapid degas. If you are going to put this type of a system on your generator, well, essentially you need to do, if you're going to do a rapid degas, you need this type of device. Otherwise, you're going to shock that generator by putting cold CO2 into the generator. But I think the answer to the question is yes, there are systems available that will allow you to do a rapid degas of the generator in emergency situations.
Okay, great. Thank you, Steve. That concludes today's webinar, Hydrogen Safety Best Practices for Large Turbo Generator Gas Monitoring and Purging with Steve Kilmartin and E1 Utility Systems. Please feel free to contact Steve with any additional questions you might have. E1's website is on the final slide. And remember that the webinar will be available on Energy Tech's website, www.energytech.com, if you'd like to watch it again or share it with colleagues. And if you enjoyed today's webinar, register for our upcoming presentations in November with Intech on condenser retrofits and in December with Energy Tech contributor Commander Sundaraj on performance and reliability. We will be sending out emails about registering for these webinars in the next few weeks. Until then, thanks for joining us.
Thank you.